In this video, we're going to talk about unit vectors, introduce some physics notation, and talk about how we could calculate components. First of all, a little review and some notational things. So I have two three-dimensional vectors, vector A and vector B, that you can see up here. And I'm going to combine them in some ways. So this very first thing you see, this looks like absolute value. Think about absolute value like it is distance, because that's really what absolute value is. It's how far from zero you are. Well, this is a distance, but of course, with multiple dimensions, distance means we're going to use Pythagorean theorem. So we do square root, of course, 2 squared plus negative 3 squared plus 5 squared. Okay, so this is, let's see, 4 plus 9 is 13 plus 25, so the square root of 38. That is the magnitude. For the magnitude of B, we have 0 squared plus 3 squared plus negative 2 squared. So 9 and 4, this is the square root of 13. Next, I'm adding the two vectors together, A plus B. So 2 plus 0 is 2. Negative 3 plus 3 is 0. And 5 plus negative 2 is 3. So there's the vector A plus B. So then I said, well, what's the magnitude of A plus B? So the magnitude, of course, would be 2 squared plus 0 squared plus 3 squared. So again, 4 plus 0 plus 9, it is the square root of 13. The next is A minus B. So I'm doing A and then the opposite of B, if you think about it from a geometry standpoint. So 2 minus 0 is 2. Negative 3 minus 3 is negative 6. And 5 minus negative 2 is 7. So the magnitude of that would be 2 squared plus negative 6 squared plus 7 squared. So 4 plus 36 is 40 plus 49, so the square root of 89. And finally, 2a minus 3b. Okay, so let's think 2a, so 4 minus 3 times 0, so this would still be 2. Oh, excuse me, 4. And then I'd have 2 times negative 3, so negative 6 minus 3 times 3. So I have negative 6 minus 9, so that will be negative 15. And then I have 2 times 5, so 10, minus 3 times negative 2. So 10 minus negative 6 is 16. All right. Next, a unit vector is a vector that has the same direction as the given vector, but a magnitude of 1. So essentially it's parallel. Okay? And if you remember, parallel vectors means that you can take a vector, multiply it by a scalar to create a second parallel vector. So the way to prove two vectors are parallel is to find that scalar, to say, okay, is there one number that I could multiply each component by to get the other vector? So if you can check your memory here, this is something we talked about at the end of Calc BC. This, of course, is vector A. Vector A had a magnitude of the square root of 38. If I take each component and divide it by the magnitude, this is my unit vector. Okay, so first of all I really did here was I took my original vector and I multiplied it by 1 over the magnitude. Okay, so there's why they have the same direction, because parallel vectors have the same direction. I was able to just multiply by that scalar and get this new vector. And if you can think about this as kind of, it's not a proof, but it's kind of a nice way to think about finding the magnitude of this. If I squared this, I get 4 over 38, 9 over 38, and 25 over 38. Well, 4 plus 9 plus 25 is 38. 38 over 38 is 1, square root is 1. So I've created a parallel vector, one that has the same direction, and it has a length of 1. So this is a unit vector. Okay. Now, a unit vector, in this case, this is what's called, this is physics notation. Okay. This is the x component goes on I, y component goes on j, z component goes on k. So another way, if you want to think about it like this, it's really this. That's really what this vector is. So if I find the magnitude of this vector, 5 squared plus negative 2 squared plus 2 squared, the magnitude of this is the square root of 33. Okay, but I'm going to keep it in the physics notation, since that's how I gave the problem. So it's going to look like this. Okay, so there's my unit vector. Now, what's the angle between the vector 3i and 2j? So let's first of all, and the x-axis. Let me first of all draw that. So it's got an x component of 3 and a y component of j. So it looks something like this. Okay, and I'm looking for this angle. And this, of course, okay. So if I'm looking for the angle, I could definitely use tangent, because I know the opposite and adjacent sides. And I could say, well, the tangent of theta is equal to opposite over adjacent. So theta must be equal to the inverse tangent of 2/3. And you could type that in and solve it. Now, the reason I put this problem in here is not because it's that difficult to draw it out and figure it out. I think you'd be able to do that. But I think it brings to mind that this is something that is very easy to do in 2 dimensions, but very difficult to do in 3 dimensions. If I added and I said, what's the angle between the x-axis and this vector? That would look very difficult without vectors and dot product, which is what's coming in the next couple of days. Okay, so there are some ideas here that a lot of times I think people think, why am I even bothering with vectors? I know how to do this stuff. In 2-dimensional space, we have lots of workarounds, but in 3-dimensional space, things are extended with vectors, things that you can easily leap from 2 to 3 dimensions. In vectors, it's an easy jump, but with just straight geometry or trigonometry, it's not an easy jump at all. So that's a great reason to practice with your vectors, even stuff like this that looks pretty easy. Finally, I just want to talk about getting horizontal and vertical components with motion. Okay, so you can see a ball leaves the bat with a speed of 92 miles an hour. So think about this as a kind of a component like this. This is 92 miles per hour, 23 degrees. And I want to find the horizontal component and the vertical component to this. So I would think about it almost like it's, an x here and a y here. And we're solving, basically we're saying, well, if I want the horizontal component, that's the adjacent component. So this is a cosine. This is like saying the cosine of 23 is equal to x over 92. And of course, I could multiply both sides by 92, and I'm going to just kind of shorthand it, it would look like this. That is the x motion, or the speed in the x direction, okay? So if I then focused on the the vertical component, now of course I'm dealing with the opposite, so this is the sine. Like that. And I would multiply both sides by 92, and I would have this. So my components for the motion here, and of course I'm not going to calculate it, but you could, and then you could present it with just decimals. The x component and the y component, like that.